Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will try to do relative permeability normalization and denormalization. So if we have several core samples, for example, we have several core samples, and of course from the core sample, or to be accurate, the special core analysis, if we have several special core analysis reports, from which we can have several relative permeability data, and we just want to come up with only one representative relative permeability curve, which will represent our entire field. Okay, suppose that's the case, and yeah, we will try to do exercise regarding relative permeability average, something like that. And the source from which I take this example is, of course, the great book, Tarek Ahmad, Reservoir Engineering. Okay, so if you are interested, you can go to the textbook, the very interesting textbook, and yeah, you can cross-check with this exercise that I will do soon. Okay, so here we are in the spreadsheet, and this is the game plan. To save my time and your time, I will just show you the result which have been answered. Okay, I already did this exercise and I just will explain how I can get that result. Okay, because if I have to start from scratch, yeah, it will take some time, the recording and something like that. Okay, but hopefully I can explain as many things as possible from the spreadsheet. Okay, so here we go. Suppose we have three core samples, let's say core A, core B, core C from a reservoir, and yeah, whatever, maybe it can come from three wells or maybe three depths. Okay, and let's say we only have, out of our entire field, let's say we only have three core samples from which we generate the spatial core analysis and we take the relative permeability data. Okay, so for core sample A, the thickness of the core sample is 1 feet, and the absolute permeability is 100 millidarcy. And based on the laboratory measurement, we know that the critical oil saturation, okay, is 0.35, and then the critical or core water saturation is, this 0.25. Or maybe it's not critical oil saturation, it's residual oil saturation. Okay, so SOC is the residual oil saturation, but in Tarek Ahmed book, he used critical oil saturation. Okay, and the second core sample B, again the thickness is 1 feet, but the absolute permeability is 80 millidarcies. The oil saturation, residual oil saturation is 0.28, whereas the water saturation 0.30. Okay, and the core sample C, thickness 1 feet, and then permeability 150 millidarcies, and the critical oil saturation or residual oil saturation in this context 0.35, and connate water saturation 0.20. And here is our relative permeability package. Okay, okay, from core sample A, core sample B, and core sample C. Okay, and then here I use yellow color to denote the critical saturation. Okay, like this one, this is the 0.25 connate water saturation, and the relative permeability of the oil at this connate water saturation is 0.85. Okay, and on the other hand, at residual oil saturation or saturation of water of 0.65, the maximum relative permeability of water 0.4, and so on and so forth. Okay, so maybe you're a student, yeah, mm, the data that you will use in your class is, of course, maybe from textbook or maybe from literature. But if you are a new engineer, okay, watching this channel, whatever, okay, uh, you can get the SCAL report, Spatial Core Analysis report, maybe from several reports from one reservoir, and you can gather the relative permeability curve data, and then you can do exercise like this. Okay, so let's extract one representative relative permeability curve from these three core samples. Okay, I'm going to follow the steps from Tarek Ahmed book. Okay, and I think some experts have their own approach, but yeah, I will follow for the base case the Tarek Ahmed approach. Okay, so first we need to calculate the normalized water saturation. Okay, normalized water saturation for each core sample. We call this SW star. Okay, and the calculation is very easy. Water saturation minus Connaught water saturation divided by 1 minus water saturation minus critical oil saturation or residual oil saturation. And it's easy. Okay, for core A and core B, we do not use 0.20 because the Connaught water saturation start from 0.25, right? Okay, and then we just use this formula. Okay, I take the water saturation from this column, Connaught water saturation from this data, okay, 0.25 minus 1 minus Connaught water saturation minus residual oil saturation. And don't forget to use dollars because we will use that value again and again. Okay, so we get that and then we just drag like this. Okay, the same approach we do for core sample A, B, and C. And here I take this, okay, from the given data that I show you earlier here. Okay, so I just copy and then paste here, okay, to make me more comfortable to take this data. Okay, so it's very easy. SWC, SOC already provided. And most of the time you will know based on the SCAL report. Okay, so we get the normalized water saturation that we will use for the subsequent calculations. Okay, second step, step 2, determine relative permeability values at critical saturation for each core sample. And we already know that, right, from the data given. So here, the relative permeability at critical saturation, it means relative permeability of oil at Connaught water saturation. And vice versa, the relative permeability of water at residual oil saturation. And it's very easy. We just take from the data given. So the maximum oil relative permeability will occur at Connaught water saturation. And that's why the value is 0.85. And on the other hand, the maximum water relative permeability will occur at residual oil saturation, which is 0.4 from the data given. Okay, so that's why I use yellow color here to make it easier for me to distinguish the relative permeability at critical saturation. Okay, so you get this value, very easy. And then we get this. Okay, we need to calculate relative permeability of oil bar. There, the bar, it means its average at SWC, Connaught water saturation, and vice versa, the average relative permeability of oil at residual oil saturation. And Tarek Ahmed provides the formula. It's very easy. So to get this, don't forget bar means is average. Okay, and we will look at the relative permeability of oil at, you know, Connaught water saturation. So here sigma means summation. Okay, this should be I equals to 1 through I equals to n. So in this case, we have n equals to 3 because we have 3 samples, right? We have n equals to 3, and let me, okay, color it. Okay, so we have core sample A, core sample B, core sample C, and within this bracket is the calculation or the multiplication between thickness, the absolute permeability, and the relative permeability of oil at Connaught water saturation for each sample, and divided by the summation of thickness multiplied by the absolute permeability for each sample. And we also do that for the water at residual oil saturation. And it's very easy. Okay. So first, all right. So maybe like this, or maybe like this. Okay. I'm going to, okay, move them like this. Okay. All right. So provide thickness, provide absolute permeability for each sample. There you go. And provide this data, which we already have in previous step there. Okay, so I just use equal so that I can take this value here. And here I take from that. Okay, so prepare for each core sample. And then we just need to calculate like this. So for average relative permeability of oil at Connaught water saturation, it's very easy. So thickness multiplied by absolute permeability multiplied by KROS at SWC. Okay, and then you sum them up with core sample B. This is the formula, and core sample C. And everything, you put them into one bracket, one parenthesis, and everything there, the nominator, okay, divided by the numerator, okay? And the denominator is the multiplication between, thickness and the absolute permeability, and then you also sum them up to get this, the average relative permeability of oil at Connaught water saturation. Okay. Why do we need to do this? Because we want to give greater weight, greater weightage factor to the core who has or which has highest permeability. We want to honor more the core that has greater permeability. Yeah, because it's about permeability. Okay. At the end of the day, it's still about permeability. Don't forget, we are talking about relative permeability. So of course, core sample or the rock body which has greater permeability will affect the performance more, right? More significantly influence the entire performance. So that's why we need to calculate the thickness and then the permeability, the absolute permeability. And also we want to give more weightage factor to the core that has more thickness, longer thickness. Why? Because the longer core will be more representative compared to the shorter core. Okay, but in this case, we all have 1 feet for each core, so they are the same. But we have distinction in terms of, absolute permeability. So the average relative permeability of oil at Connaught water saturation is 0.906, whereas the average relative permeability of oil at residual oil saturation is 0.402. Okay, so far so good. And then we need to calculate the normalized relative permeability of oil. We call this KRO star and KRW star for all core samples. And again, the computation is very easy. It's just KRO divided by KRO at SWC at, Connaught water saturation. And normalized relative permeability of water, KRW star, is relative permeability of water divided by relative permeability of all water at residual oil saturation for each core sample. So here I have the true water saturation, and we have the normalized water saturation. Okay, and we can calculate the normalized relative permeability of oil, normalized relative permeability of water for each core sample. So like this, we have this already, the normalized water saturation. We can take that from the previous table. Okay, so you see I have this. So I take this value from the previous table. And to calculate this, I just divide the relative permeability of oil from the previous table, C8, C8 there, okay, divided by this, KRO at Connaught water saturation for that core sample, okay? We haven't used this average yet, okay? So again, you can drag this like this, and you do that also for the water. You go to the original relative permeability of water data there, and then you divide that with relative permeability of water at residual saturation at that particular core sample. So you get this, and of course you get the table. It's quite easy so far. Okay. Okay. And you do this exactly the same approach for each core sample. Okay. And then you need to plot the normalized value of KRO star and KRW star versus the normalized water saturation for each core on a regular graph paper. So we will use the linear scale, and we do that here. So the horizontal axis is let me make it bigger. The horizontal axis is the normalized water saturation. On the left, I use the normalized relative permeability of oil. And on the right, I have the relative permeability of water normalized. And we just take that, for example, here, I take that from this. For sample B, can also do this. Okay, and then for this, I take that for the B core sample, relative permeability of water, normalized. So here, I take it from here. Like this. Okay. And if you want to look at it, okay, so here I touch this, you get that from the table. I touch the next curve, you take that from this table, and the next, I get that from there. There, I get it from here. There, I get it from there. There, I get from there. Okay. All right. Oh, so and then the step 6, select arbitrary values of normalized water saturation and calculate the average relative permeability of oil normalized and normalized relative permeability of water. So we are going to have, first, we want to generate a curve. Okay. We want to do regression. Okay. To get the correlation between normalized water saturation and normalized relative permeability of oil, and normalized water saturation with normalized relative permeability of water. So my approach, we haven't used this for now. So my approach is like this. So to make it easier for me, I copy that and then I paste here. And I want to get for the core sample A. So I'm going to delete this one and then delete this yellow and then delete this gray and then lastly I think here. So I have core sample A remaining on the curve, okay? And then like this, I can just right click and then add trend line, okay? So you see, first I have a linear calculation there, linear curve. It's not curve, it's a line, right? And I can display the equation on chart, okay? But don't forget it's still linear. And then I can also show the, oops, format trend line, display R square if you want, okay? Actually, from mathematical point of view, this approximation using linear line, right? It's already good because the R square is 0.9983. But you can still improve it by using polynomial approach. Okay, polynomial approach such that the trend line approximately or very closely approach the line, the real data. And from that we get this, you know, correlation. So using the correlation, I can use my arbitrary normalized water saturation to calculate the normalized relative permeability of oil. And you do that the same exact approach with the water relative permeability. I right click, add trend, and then use polynomial, okay, to the order of 2. Sometimes you need up to maybe order of 3 and maybe 4. But here in this case, with order of 2, second order, we already have R square, which is very good, 0.9997. Okay, let me put the new curve here, and then you can see that the one I made previously is exactly the same. Okay, so I can delete the new plot. Okay, good. And then use this mathematical equation for the oil and for the water to calculate the normalized relative permeability of oil and normalized relative permeability of water at arbitrary normalized water saturation. Arbitrary here means you can just put 0.1, 0.2, 0.3 up to 0.9 if you want, but you can also put 0.12, 0.247, 0.503 if you want. But to make it tidier, I just use 0.1 up to 0.9. Okay, and I can use the correlation there, minus 0.1472 multiplied by normalized water saturation. It's order of 2, okay, second order, and then minus 0.8435 multiplied by water saturation normalized plus 0.9969, and then you get that. So you get this data for the normalized relative permeability of oil and normalized relative permeability of water at each normalized water saturation. And this is for core A. You do that as well for the core B, and you do that for the core C. Based on my calculation, this looks a bit weird, but never mind, because you just do the simple calculation to get and to construct this curve. But you can still, approach this relative permeability curve with the trend line. Okay, so you get that, and then what else? We need to select arbitrary. Okay, so far so good. And then, okay, we also need to calculate now. Okay, we now need to calculate the average normalized relative permeability of oil and average normalized relative permeability of water. Just like what we did before, but before we haven't used the normalized relative permeability. In this case, we will consider or we will use the normalized relative permeability. But the calculation is exactly the same. We have summation there and summation at the denominator, okay? And both for the relative permeability of oil and relative permeability of water, okay? So for the numerator here, it's the summation of the multiplication of thickness multiplied by absolute permeability and the normalized oil saturation for each core sample. And for the denominator, it's the summation of the computation between or the product between the thickness and the absolute permeability for each core sample. So again, I borrow the thickness and the absolute permeability for each core sample. Okay. And I just use this. Okay. KRO star at A and then KRO star for B and KRO star for C. Okay. I just take the previous result. Okay. Here I take that from here and there I can take from table B for the normalized relative permeability. And lastly, here I take that from there. Okay, so you create this, it's very easy. And then you just, in my case, I just calculate it step by step. So I use this exactly the same for the normalized water saturation. And I just calculate thickness multiplied the absolute permeability multiplied by the normalized relative permeability of oil. I do that for each normalized water saturation, for each core sample, for each phase. Oil, water for core sample A, color it yellow, and then oil, water for core sample B, let me color it blue, and oil and water for the core sample C, let me color it green. Okay. All right, so now we can calculate the relative permeability, normalized relative permeability of oil and water average. And I will use this formula. Let me put it there. It's very easy. Let's focus from this range. Okay, and then, yep. So there, the, the summation between this multiplication for each core sample, A and B and C, for each phase, oil in this case, and divided by the summation of the, the product of thickness and the absolute permeability. So you cut this and then you do that for the water. Okay. And then you can construct the, this. The horizontal axis is the normalized water saturation, and the vertical axis are for the, normalized oil saturation or normalized relative permeability of oil and normalized relative permeability of water. Okay, And yeah, to make it better, maybe I can color it green, and then this for the water, I can color it blue. Okay, and then yeah, for the marker as well, let's fill it with blue. Okay, and then this, let's color it green instead. Perfecto. All right. So it's very easy so far. And last, I think it's when, okay, so this is the normalized version of the water saturation, oil relative permeability, and the water relative permeability. But we need to denormalize it, okay, to come up with the representative, relative permeability curve. And we do that. Here it's a little bit tricky. So, okay, so you have core data, you have several core data, but you also have field performance. You sort of have, the one value that you think will represent the field better. In this case, in our example, Tarek Ahmed used in the example that based on everything, based on your analysis, your experience on the field, based on all the core data, based on the field performance, you believe that this value, the residual oil saturation of zero point 0.3 and Conat water saturation is, suit your reservoir better compared to individual core sample. Okay, so we will use this, the residual oil saturation of zero point 0.3 and the Conat water saturation of 0.27 to denormalize our relative permeability data which we normalized previously. Okay, so again, in your practice, maybe, or in most cases, you will have such value like this. A single value that you think from everything that you have, data, core data, field performance, discussion, everything, you come up with this value. Okay, and after you get this, okay, after you know the residual oil saturation and Conat water saturation that suit your reservoir better, you can then normalize. And we do that using the desired formation residual oil saturation and Conat water saturation. We will denormalize the data to generate the required relative permeability data. Okay, so it's very easy. Yeah, I take this 0.3, Conat water saturation 0.27, and again, I will use this, the relative permeability of oil at Conat water saturation, which I calculate previously, and the average relative permeability of water at residual saturation. Okay, so first we denormalize the water saturation using this computation. So water saturation is the reverse calculation from the previous step. So water saturation is the normalized water saturation multiplied by 1 minus Conat water saturation minus residual oil saturation, close, and then plus Conat water saturation. Okay, so you get that here, and then you just drag it like this. And then for the average relative permeability of oil normalized, okay, and the normalized average relative permeability of water, you denormalize using this formula 5 and formula 6. So the denormalized relative permeability of oil is the average normalized relative permeability of oil multiplied by the average relative permeability of oil at Conat water saturation here. So I just take, the average normalized relative permeability of oil multiplied by the average relative permeability of oil at Conat water saturation. And then you just do like this. And the same thing for the relative permeability of water, the representative or the denormalized relative permeability of water is the average normalized relative permeability of water multiplied by the average relative permeability of water at Conat water saturation or at residual oil saturation. Sorry. You do that, and then you just drag like this, and then you can construct from you can construct the plot, the representative, the single representative relative permeability curve to represent your entire field. You can construct like this. Again, the horizontal axis is the true, the denormalized, the water saturation. And for the vertical axis, we have the true, the denormalized relative permeability of oil and relative permeability of water. Very easy. And let me change the color to make it better. Okay, and this one for the oil. Okay, all right. So here you go. So we have discussed how we can extract a single representative relative permeability curve that will represent our reservoir from several core sample data, from several relative permeability data that we obtain from special core analysis report. Okay, so that's all. I hope you enjoyed this video. I hope this video is useful. Thank you so much for watching and see you again in the next Eng-Man videos. Thank you.